Thank you and welcome to this YouTube channel. This is a Brilliant Online Academy. Today we are going to talk about moles, titration, volumetric analysis. We are going to do some examples which involves the calculations in moles regarding the titration. Titration, we are going to maybe dwell much about it, but kindly subscribe to this YouTube channel, click the notification bell, and also like the video, share with friends. During this holiday, I want us to demystify this chemistry so that whenever you go back to your respective schools, at least you'll have an easy task or easy time to at least to revise for your examination. Moles is the one of the topics which most of the students think that it is difficult, but truly, this topic is the easiest. I want you to love it, like it, and ensure that you do more examples on moles so that at least you will be able to remember, grasp whatever you learn, and it will automatically stick into your permanent brain. It will be stored permanently. The best is to do much about these moles, and trust me, you will love this topic. So most of the one that I'm going to discuss, we are going to use the formulas that the formulae that we have used in our previous video, at least to make the calculations easier for you to understand and to master. Again, this topic, our lesson today is very important because it is always being tested in paper 3 chemistry under the practical, that is moles, titration, I mean. So let's see this one. So the topic for today, I've said that is the volumetric analysis, and also we can call it the titration. Then we have, we have the volumetric analysis. The titration is just the process of determining a known concentration of one reactant from a known concentration and a volume of another. So we'll be able, in the titration, our aim is to identify the concentration of a known solution using the known concentration and also the volume of another reactant that maybe will be given. So we are identifying, we should be able to determine the unknown concentration or volume of a reactant using the known concentration of the another reactants of those solution. Then the reaction takes place in simple mole ratio of reactant product and products. In maybe if you are told you are provided maybe with a solution A, and that solution A is sodium hydroxide, another one is hydrochloric acid, then these two solutions will react to produce some, to liberate some products. So those products and the reactants, they will bear simple ratios to mean just a stoichiometric equation, which balances the reactant and the chemical, the products side. So that is just a matter of balancing the equation. Very good. Then another one, knowing the concentration, volume of one reactant, the other can be determined from the relationship. So if you know a concentration or the concentration or volume of the reactant, you can be able to determine another product or the reactant using the what? the relationship that we'll be able to provide, and the relationship is this one. We have molarity or the concentration 1 times volume 1 over the number of moles 1 should be equals to the concentration of the second solution times its volume, that is the volume of the second concentration, over the moles of the second solution. I think so M1 is just molarity of the first reactant, then M2 is the the molarity of the second reactant. Then we have the volume 1, which is the volume of the first reactant. We have volume 2, which is the volume of the second reactant. Then we have N1, which is the number of moles of the first reactant from stoichiometric equation, the balanced equation. The N2 is just the number of moles of the second reactant from stoichiometric equation. That is that. Now let's see the next one. We'll be able to discuss the solution of a known concentration is referred to as standard solution. So maybe you can be told to prepare a standard solution. So when maybe the teachers are preparing the solutions to be used or the reagents to be used in titration, the solutions are standard. So those the solution of a known one, the known concentration, they are standardized. So they are standard solution that maybe your teacher or your lecturer has, or the lab technician has prepared or as standardized. So that is standardized solution. The apparatus to be used in titration: 1, we can use the pipette, we will use the burette, and we will use the conical flask. How to fill the table, very much important. How to fill the titration table. Here, the filling the titration table comprises of 5 marks, rather 4 marks, that you should be able to put in your pocket even before touching even the apparatus or the solution given or the reagents given. Because 1 is much easier to know how the titration table is filled. One thing that you should be able to know: fill the table with realistic values. That is the value, because the realistic values. Because 1, we know that the burette reads from 0 to 50. So any value which is beyond 0 or below, not beyond 0, but below 0 is unrealistic. If you get any negative values, that is unrealistic value. Or if you get any value beyond 50, like 51 or 50.5, 50.20, 50.1, those are unrealistic values. So the values that you should get should be from 1 up to 50. The values that you should be filling your table with should be read from 0, from 1, I mean, from 50, and you should be able to know that. You can't read 0 because when you are titrating, there's some volumes or volume or the amount of solution inside the burette will be dripping down. So therefore, you can't get a 0. So 0 is just initial. 0.0 is just initial value before titrating. Then we have another one: fill the table with consistent number of decimal places. So the number of decimal places should be consistent in a way that if you have chosen to use 1 decimal place, then you should use it throughout the table. Don't mix the number of decimal places. So that is what also should be able to know. For instance, let me take a pen here. For instance, when we have 0.0 as your initial, then maybe the tighter value you can't write maybe 26 or 0.20 like that. This will be wrong. It will be inconsistent because here we have 1 decimal place and here it is 2 decimal places. So ensure you know about that. And again, one very important message that you should take home now, if you're chosen to use 2 decimal places, ensure that the last digit should be either 0 or 5. That is, you can't write 26.23 or 26 or 27 or 29 or 28. This last digit should be either 0 or 5. That is 26.20 or 26.25. So those are things that you should be able to know. The decimal should be consistent. That is, if you have chosen to use 1 decimal places, use it throughout the table. If you have chosen to use 2 decimal places, also use it throughout the table and ensure that the last digit after the decimal should be 5 or 0 when you are using 2 decimal places. Very magnetic. Another one is the tighter value to be averaged. Very much important. The tighter value to be averaged should be in the range of positive or negative 0.2. What would this mean? This is now the principle of averaging. In the principle of averaging, the tighter values are the values which you have gotten the last value in the table. So maybe, for example, if the first one you got 26.2, the other one was, the second one you got maybe 26.6, then the next one you got 26.5. So we have 26.2, 26.6, 26.5. So the values that you should get the average should be within the range of positive or negative 0.2. So check this one out. What is the difference between 26.2 and 26.6? You realize that it is either positive or negative 0.4. What is the difference between 26.2 and 26.5? You realize that the difference is positive or negative 0.3. But now what is the difference between 26.6 and 25.5? The difference here is 0.1. And that is now to mean this one is not within the range. So therefore you will take this one and this one, you add them, then you divide by 2. Because their differences are in the range of positive or negative 0.2. And Mark, you know that if your values in at the national marking, if your values are in the range of 0.1, you will get 1 mark. But if your values are in the range of the tighter values that you are getting the averages, the average I mean, are in the range of positive or negative 0.2, then you will be given a half a mark. So the accuracy is much more important. So when you are doing that, make sure you be very accurate doing titration. because some as a student might decide not to do the experiment and just follow the steps that I've given to fill the table. Ensure that you use the consistent values, you use the realistic values, you use also the values, the tighter values that you are getting. The average should be within the range of 0. So take 0.1 for you to get 1 mark. You feel that way. The only thing that will miss is now the accuracy, when because the last value that you're getting, or the tighter values, if any of the tighter values that you have gotten are in the range of positive 0.1 of the school values that the teacher will be doing, you will be marked and you will be given 1 mark. But if it is in the range of 0.2, then you will be given a half a mark. But if it is out of that range, then you will only lose that 1 mark for the accuracy. Let's proceed on now. We check one of the examples. We have the choice of indicators, the indicators that are used. When you are titrating a strong acid against a strong base, we use any indicator. But when you're using strong acid against weak base, we can use screen methyl orange or methyl orange. But when we're using weak acid and strong base, we use now phenolphthalein. And you should know the colors. So we have different types of titration. The first one that we are going to discuss is the back titration. What is this back titration? So it is a titration analysis which involves the reaction of a given amount of a sample with a given volume of solution of concentration or molarity is excess. The excess is titrated against a standard solution. I've said it is the titration analysis which involves the reaction of a given amount of a sample with a given volume of solution of a solution of concentration or molarity is excess. The excess is titrated against the standard solution, just the way we are going to see. First example here, you are provided with one solution M, and this solution M is 0.5 molarity of hydrochloric acid. We have solution N containing 5.3 grams of a metal carbonate, that is X carbonate, dissolved in 250 distilled water in a volumetric flask. We also provided with an indicator that is methyl orange, because we have the acid under the base. Then we have titration apparatus also you have been given. Then you are also been given that sodium is equivalent to 23. Then carbon 12, then oxygen 16. So I want you to write that. You write that example because there are some values or information that will extract from it. So that you try doing as we proceed on. You are required, one, you are required to determine the concentration or the molarity of N in 1 moles per dm cubed or grams per dm cubed. Then you also require to determine the relative atomic mass, that is RAM of X. So this is the procedure now. Pipette 25 cubic centimeters of solution N and transfer it into a conical flask. Then add 2 to 3 drops of the indicator get the concordant values, that is the values that are close to each other. Suppose you obtain the values in the following table. So what you do, you pipette, you know, the pipette mostly reads from 25 ml. So then there is a mark there. There is also a mark. You can use a pipette filler or use your mouth to suck and ensure that the volume that you're sucking should reach the mark on the burette, on the pipette, I mean, sorry. Then transfer that solution into a conical flask. Then you add 2 to 3 drops of the indicator, where we were told that the indicator that we were given was methyl orange. You add 2 to 3 drops. Then you do this 3 times for you to get the values which are concordant, or the values which are close to each other. Then maybe we did, mine I did and I got this. This is my table. The first one, we have the initial. This table, when you are given an exam, it is always empty. So you are the one to fill all these values that we have gotten here. So the first one, I placed my initial value to be 0.0. That is before doing any experiment at the beginning. Then if I titrate, then the color changed at the volume of 22.0. So that is now the volume of the final reading of the burette. So after this is my burette, for example. So here is 50, here is 0, 15. So before I do anything, it is 0.0. Ensure that you fill the table with decimal places. Whether you got it 20, make sure it is 20.0. So there, I got that. I titrated because also there is that conical flask with solution N. Then here you fill this with solution M, which I think was a sulfuric 6 acid, hydrochloric acid. Then you titrate, maybe then the color of the solution in the conical flask due to the methyl orange changed at 22. So to me now, that will be the final burette reading. So you write it there. For you to get the volume used, it is always the final minus the initial. So 22.0 minus 0.0, you get 22.0. Then the initial value, now I'm beginning. You can either decide to fill it again, or you begin from where you had reached. So when you are beginning there, ensure that the one that the content remaining will be able to give you the next value before it runs out from the burette. But assume that you got 27, then you have to fill it, because even 27 is more than 15. So because it is 22, we can say that that will be now our initial value in the second titration. Then we titrate, then maybe run up to 43.9. So to get the final or the volume of the acid used, it is just 43 minus 43.9 minus 22.0, you get 21.9. That is that. Then you go to the next. Now you have to fill it because you had reached 43. So you fill it again up to 0. Then the initial will be 0.0. Then maybe it reads up to 21.8. Then your volume of the acid will be 21.8. Very much important. So So when I come back, sorry, let me come back here. You can see here very well. Here, we said that the titration, we are getting the concentration of an unknown using the concentration of known one. So here we are given the concentration and known concentration of the hydrochloric acid, which is M. Now we have to get the concentration of the what? Of N, of unknown. We don't know its concentration. That's for X carbonate. So that is what I wanted to explain for you so that you'll be able to know that. And now the first question, calculate the average volume, and it will always be the first question. You calculate the average volume of solution M used. Show how you get your answer. So this is, now you bring your principle of averaging, Let's check the titer values. We have 22.0, we have 21.9, we have 21.8. Now check, what is the difference between 22.0 and 21.9? The difference there is 3. It can be either positive or negative 3. Then compare this one again, this and this. The difference there will be positive or negative 4, 0.4 I mean. Then you know that is not the range now that we can use. Now let's compare this and this. 21.9 and 21.8. The difference is either positive or negative 0.1. Therefore, we'll now use this one, because if you compare this and this, the values or the difference is beyond 0.1, 1 or 2, 0.2. So we'll get that clear. The only values that you can get, the average, the titer values, they are the titer values which are in the range of positive or negative 0.2. That is that. So let's see. So we'll what we'll be able to get. So we'll take now 21.9 plus 21.8, then we divide by 2, we'll be able to get 21.85 cubic centimeters. Sorry. Then write the chemical equation. The chemical equation, you write the chemical equation of what is in the burette plus what is in the pipette or in the conical flask. What is in the conical flask is what is reacting with what is in the burette. In the burette, we have solution N, which was 0.5 hydrochloric acid, and also we have the one in the conical flask, which is X carbonate. So the carbonate plus acid, I know you should be able to know that you get salt, you get carbon dioxide and water. So those 3 products, that is what should come to your mind. So we'll have HCl plus X carbonate, which can give you X chloride plus carbon dioxide plus water. Then you balance it. It should be a stoichiometric equation, which looks like that. Then that is that. So this X will combine with them, an ion from this, from the acid, that is chloride ion combines with this X ion to form X chloride. Because if you check here, why do we say that it will be like this? Check here, check. You can even make this one in to be in separate ions. So we know that carbonate is written like this, and it has 2. And X, because these 2 came here and 1 came here, then we know that the valence electron of X is 1. Therefore, that is why we won't have anything in front of chloride. That is what you also should know. The chloride also has always or has one valence electron. The valence electron is that electron that can be lost or gained in a chemical reaction. So that is that. So this one also has 1. So 1, if they swap, they will be just, the ratio will be 1:1. And we have water, then in balance here, we had 2 X atoms. So here must be 2. Then because of 2 there, chloride will write 2 here to balance it. Hydrogen 2, and now the equation is balanced. Very good. Then here now we are told to calculate the moles of the acid used. Calculate the moles of the acid used. In our previous class, we said that moles can be gotten as molarity times volume used over 1,000. And if you check our volume used for the acid is this one. That is that. And its molarity, we know its molarity, which was 0.5. Then now we multiply 0.5 times volume, which is 21.85. Then we divide by 1,000. That's the way it has been done here. We'll be able to get 0.01 moles of hydrochloric acid, as simple as that. If you use the formula, it will be much easier. So we have said that the moles can be gotten as molarity times the volume used. And you can see here, this is the volume used of the acid. Then we divide by 1,000, and we say the reason why we are dividing by 1,000, we are converting that volume into liter. Very good. And the next one. Calculate the concentration. The concentration of X carbonate. The concentration here, first thing that we should be able to know, the concentration is more or less the same as molarity. So we can get the concentration in grams per liter. We can get the concentration in moles per liter, just the way we were required to determine. Those are the things that we are required to determine. So calculate the concentration of X carbonate. Use the stoichiometric equation to get now the moles, because the concentration is given by moles times what? Times 1,000 over the volume used. And the volume used of this, we knew that the volume that was used here was 25. That is what we pipetted. Now get the moles using the mole ratio. So you have to write that equation that we wrote earlier, will be able to help us get the moles of the carbonate, the X carbonate. So let's see this one. Sorry, I've given the answer up to down. So the mole ratio will be 1:2. Let me take you back so that you will be able to understand that. Where we wrote the equation. So for us to get that, we use the mole ratio. The mole ratio of this, the mole of this carbonate is 1 that reacted, and the mole of the acid that reacted are 2. So the mole ratio here will be 1:2. And we know the moles of the acid, which is 0.01. So if 2 is equivalent to this, now 1 will be what? So it will be 1 times this one divided by 2, which will be able to give you 0.005. So that is what we have said here. So if 2 is equals to 0.01 moles, so 1 will be equivalent to what? So it will be 1 times this divided by 2 to be able to get 0.005. 0.005 moles of X carbonate. From there, we can be able to get now the concentration in moles per liter or moles per dm cubed. So I said very well, leave alone all these writings which are written here. You can just get whatever I'm saying, then you will be able to understand it. So now moles, or the molarity, I mean, I said the molarity in our previous presentation or lesson, we said that molarity is also gotten as molarity, which is denoted by capital N, is given by moles times volume used over, not volume used, but multiply by 1,000, sorry. Multiply by 1,000 over the volume used. So in this case, our moles we have gotten to be 0.005. Then you multiply by 1,000. Then you divide by the volume used. What is the volume used for this? We were told to pipette 25.0 cubic centimeters of solution M, and that solution M is the X carbonate. So that is the volume that was used. So you divide by 25. Then from here, you will be able to get the moles or the molarity, which is 0.2 moles per liter. Moles per liter, which is the same as moles per dm cubed. And we're told to get that at first. Thus, that is one of the what you are required to determine. Very good. So that is that, as simple as that. Why do we say it per dm cube or per cubic centimeter or per liter? Because of this 1,000 that we have converted this volume into liter. So that is that. Then again, we can also get that moles. We can also get that moles. We're also told to determine the concentration, I mean, in grams per liter. And we were given the mass. So this is the first one. We were also given the mass of what we call the carbonate, which was 5.3 grams. And this 5.3 grams was in 250 cubic centimeters. So what of 1,000? What of 1,000? So we get the moles of the concentration of this one, 1,000, where we'll be able to get that it is 5.3 times 1,000 over the volume used, which was 250. So this 250 will help us to get the concentration of the carbonate in grams per liter. In each liter, how many moles are required in that concentration? So therefore, we'll be able to get this one, that is 21.2 grams per liter or per dm cubed, not grams, but 25. In each liter, we'll have 21.2 grams of X carbonate. I want you to understand that. We were told very well that 5.3 grams was dissolved in 250 cubic centimeters. So to mean in 250 cubic centimeters, we have the solute of X carbonate, which had a mass of 5.3. So what of in a liter or in 1,000? So therefore, we'll say now how many grams of that solute will be in 1,000. We'll get that it is 21.2 grams. And now in 1,000, that is 1 liter or 1 dm cubed. So to mean now we'll say 21.2 grams per dm cubed or a liter. Very good, just easy as that. Then we are here asked again, calculate the mass of the carbonate. And I've said here, note, we express the concentration. We express the concentration of X carbonate solution N in moles per dm cubed or grams per dm cubed. So how do we calculate the mass? We can calculate the mass by using the formula that we discussed earlier, where we said mass is given by moles, can be gotten as moles times mass. Calculate the mass of the carbonate. The mass of the carbonate, we know that mass is given by, I think the question was asking the molar mass, because the mass of the carbonate, this one we were given to be 53 or 5.3 grams. And now the moles of this one also we had. So the question here should be asking for molar mass, not mass. So you can correct that. So calculate the molar mass of the carbonate. And now the molar mass molar mass is gotten as mass over moles. So moles of the carbonate go to be 0.005. Then you divide 5.3 divide by 0.05. Just the way it was done here. So we know that we have the concentration here. That is, if you use this method, I think it will take you really very far. There is also a formula that I want you to also understand. If we leave alone the other one, there is a formula that says that molarity is given by grams per liter over, or grams per liter over relative molecular mass. Grams molarity of this one we can get using its we had calculated already, not we can get. We had calculated its molarity to be this one. Let's take you back. The molarity of this was this one, 0.2. Very good. 0.2. Yes, 0.2. So molarity is 0.2. So that this is also a formula that you should master. Then grams per liter here we got to be 21.2, I mean, over the gram for the molar mass. So when you cross multiply, you realize that it will be 2.21, I mean 0.2 divided by 0.2, which will give you 106 molar mass of this. So the molar mass, you can either, the best, it has no unit, or we can express it as in grams as well. So that is what I want you to understand there. So that is the molar mass of the carbonate, and that is what we were to calculate, the molar mass of that, which is 106 grams. So master this formula, or you can use the one that I was telling you, that molar mass is given by moles times the moles times the mass. You will still get the same answer. Then another one, now get the RAM of X. The RAM of X, which is in the carbonate, because carbonate of X is written as this one. So hii total yake mass, the total mass of X carbonate is 106. So the RAM of all this. So what of for X alone? So we'll have 2X plus carbon is 12 plus oxygen 60 times that is 48. Should be able to give us 146. So you add this plus this, then you subtract the answer from this, then you divide the answer by 2. That's the way it has been done here. So where you add that, it will give you 60. That is 12 plus 48 is 60 is equals to 106. Then you take this 60 the other side, that is 106 minus 60 is 56. Then you divide your 56 by 2, you'll be able to get 23. As simple as that, and that is the end of that question. So we have actually we have determined the what we are required to determine the concentration of M in grams per liter and also in moles per dm cubed. And also we have determined the RAM of X as required. So in our next lesson, we'll also go to example 2, which now deals with the 2 titration tables. And because I don't want to make it long, I want just to understand that, then we'll now go to example 2 using 2 titration tables. Then thank you for watching. Kindly subscribe, hit the notification bell, so whenever I drop a new video, you'll be able to be notified. And let's walk this journey together, and may God bless. So if you have any question, just comment, give your comment, then I'll be able to handle the question professionally.